Many of you are at the beginning of studying. Maybe you won't study physics or mathematics, but I want to tell you something which is very fundamental, very powerful, and I think has a big influence in the future in science as well. But for some who haven't taken too much math in high school, maybe it becomes a bit challenging. So whatever the situation is, if there's something you don't understand and you can't follow, then please let me know. So first, let me briefly quote from the introduction of the lecture script of Professor Lenesto. And he says the following: Clifford algebras, that's what you're going to learn about, are algebras of geometries, the geometry being determined by a quadratic form on a linear space. You'll learn what all that means today, so don't worry about it. Clifford algebra is by definition the minimal construction designed to control the geometry in question. So you're like an engineer in front of a problem and you should design a solution, and like for space travel it must be the minimum solution, minimum weight, minimum energy use, etc. And the claim here is that's what you can achieve when you're faced with a geometry and you want to control it and manipulate it mathematically. What you should use, the preferred tool with the best design, is Clifford algebras. In geometry, information about oriented subspaces can be encoded in blades. You'll learn what is a blade soon as well. And these blades can be added and multiplied. So you are familiar perhaps with vectors. And so this is just one dimension, and you know how, perhaps you know how to manipulate vectors. Now in physics, the concept of Clifford algebra as such, or in the form of matrices, that's what you can also use if you like, or put it on a computer, is a necessity in the description of electron spin. So you'll find a number of textbooks saying Clifford algebra and spin. And anyway, if you open any quantum mechanics textbook and they go into the spin description and they do a somewhat thorough treatment, they'll eventually mention Clifford algebra. Without Clifford algebra, you can't give a mathematical sound description of spin in the end, and that the quantum nature of the electron is very, very fundamental. So Clifford algebra is a natural algebraic tool for controlling subspaces, rotations, and spins. Today, Clifford algebras are used in sciences such as molecular chemistry, electromagnetism, as well as engineering applications such as robotics, computer vision, and virtual reality, and many other fields as well. Okay, now let me just go and start to explain. I try to start at a very elementary level today. Okay, consider a plane like the plane of the blackboard. And a plane we can describe by a pair of numbers. So that is a real number and another real number, a pair of real numbers. And this space of pairs of real numbers, we call them x and y, and each is just a real number. So you have that both of them, x and y, they are real numbers. So that's how we start. And then we introduce for this pair of real numbers what's called in mathematics a linear structure. So what does that mean, to have a linear structure? It means you can add two pairs of real numbers, and you can multiply a pair of real numbers by another real number. So that is, if you have the first pair, x1, y1, you can add another pair, x2, y2, and you get a new pair of real numbers, that is x1 plus x2 and y1 plus y2. And then with a general coefficient, lambda, element r, you can do scaling. So this is addition, and the next is scaling. And now scaling. Yeah. So lambda times a pair xy. In scaling, it means simply each component is multiplied, scaled up or scaled down by lambda. So that's a linear structure, and that makes this pair of real number into a linear space, and that's then called R2. So this makes it into a linear space, and this we call now R2. It's two-dimensional. And now we take what's called a basis of R2. So what is that? You take a basis, and this is E1 called and E2 of R2. And you define E1 and E2 in the following way, that E1 is simply 1, 0, and E2, as you might expect, is simply 0, 1. And then any pair of real numbers x, y can be written easily with the help of E1 and E2 as R equals x times E1 plus y times E2. And then we also can define a length of R, and we define the length of R simply as x squared plus y squared, and we take the square root. And that is, if you have here x and here y, and you take a particular value for x and for y, then the R is here, and this length here is exactly this length here of R. It's x squared plus y squared, and takes the square root. That's a Pythagorean law which can be applied here. So the introduction of the length, that means you can measure a distance, that makes the plane R2, we have what's called in mathematics, and it refers back to a very famous ancient mathematician, it makes it a so-called Euclidean plane. And it's also written as R2. And the E1 And the E2, they get names. They are called basis vectors. And in particular, they are, if you compute their lengths, they are unit vectors. Yeah. So they are also, in this case, unit vectors. Because if you compute their lengths, then you find the length of E1 is nothing but 1, and the length of E2 also is nothing but 1. Okay. So to what I have introduced so far, does anybody have a question? Yeah. It takes time to write. I mean, when you write with a chalk, it's very hard to write bold. So in the printed script here, it's bold. Yeah. But what many people do is write vector, so that they write a small arrow on top. Would you like me to do that? Some people write not R, but they write R with this small vector with a small arrow on top. Would you like me to do that?
I don't like that.
You don't like it? But maybe some people have a difficulty to distinguish a vector from a scalar. So I could write R with a vector arrow. That's also very frequent, or just R. So is there anybody who would like me, for clarity, to write R with a vector arrow? So if you like me to do that, it's not a big problem. I can do that. So please raise your hand. Yeah. Okay, then I'll switch to the conventional notation, writing vector arrows. So we start to have vectors here, E1, E2, and that's also here. Then we define a vector in terms of basis vectors, and this is the length of the vector. Here we have R, the length of R, and length of E1 here. Okay, I hope I didn't forget it anywhere. Yeah. Any other questions? This was a very good question. This one, yes? No, in mathematics this is not called bold. Even if you print it in a text like that, you don't print it as bold, you print it with a second parallel bar. And there's a special command if you do mathematical typesetting called MathBB from American Mathematical Society or others. Yeah. So in mathematics, you define so many different spaces and sets, etc. It's easy to run out of proper symbols to distinguish, etc. So I continue on the next blackboard here. For two vectors, we introduce what you may know perhaps, and this is a scalar valued product. And it gets a product symbol, one vector A with another vector B, and this kind of central or middle dot here. And you take the components of each vector, the first and the second. So you take A1, B1 plus A2, B2. And the vectors, if you write them separately, before multiplying them, A is A1, E1 plus A2, E2. And B, similarly, is B1, E1 plus B2, E2. And both of them are members of this Euclidean plane here. So this is in R2, and this also here in R2. And if you look at that product here, the real numbers A1 and B1 can be flipped. You can change the order, and it doesn't change anything, doesn't change the sign. And also A2, B2, you can change the order. So you see, there's a special property if you define it like that it is symmetric. So you could also take the first vector as B and the second as A, and you'd get the same result. Yeah. So the scalar product is symmetric, meaning you can change the order of the factors without changing the result. Now, if two vectors are orthogonal, then their scalar product vanishes. That is the definition. Yeah. Means, orthogonality means that scalar product vanishes, it becomes 0. So we write a vector A is orthogonal to or perpendicular to another vector B if A inner product B is 0. And for example, if you try that for the two vectors E1 and E2, it's very obvious. E1 inner product E2 is 1 times 0 plus 0 times 1. So you just get 0. Okay, so definitely with this definition, these two basis vectors, they are orthogonal. And so we can write E1 is perpendicular to E2. That. Yeah. So I think maybe most of you have learned about that inner product, the scalar product of vectors already. And this is also what in the introduction, when I read from the script, is called quadratic form here. This is the quadratic form. It has a kind of high-flying mathematical name, etc., but it's nothing but this inner product of vectors. So now I continue and I introduce an associative but not commutative, that means not symmetric product of vectors in R2. So now I introduce an associative but non-commutative that means non-symmetric product of vectors in R2. Now you wonder, what is this mathematical terminology, associative? Now, if you multiply real numbers, you are used to associativity, and it makes the computations very flexible, and we don't want to give that up. We want to keep that. And an example, the associative multiplication of real numbers, for example, if you take 2 times 3 times 4, you can also multiply in a different way. First 2 times 3 times 4. And here you get 6 times 4, and here you get 2 times 12. And this, in both cases, makes 24. So you say the multiplication of real numbers is associative. It doesn't matter what you multiply first. Either 2 and 3 first, and then if this is done with 4, like here, or first 3 and 4, and then with 2. So if that is the rule for these elements, you can simply write 2 times 3 times 4, and you don't need to care for writing brackets, because you know, whatever way you do it first, it doesn't matter. It's okay. So this is this associativity here. But here, in this case, you could also flip 3 and 4 in the order. It wouldn't matter. But what we do now with vectors, the order will matter, and you cannot just flip the order, as you will see. Okay. This is a kind of remark on the side about associativity. Yeah. Now, for the new product, which we are going to introduce, we request that if you take a vector r and multiply it with itself, so you square it, it should simply have as a result the length squared. So this is a requirement. So we request that if you take a vector r and multiply it with itself under the new product, and I put no product symbol here. I just say if they're next to each other, that's a new product. So this is an r squared, and this should be the length of r squared. So just a scalar and give you the length squared. Yeah, just as we have defined the length up there. And we can put that into coordinate form because we know how to write r in coordinates. So this is r times r equals, or if we have write it straight away as a square, so x e1 plus y e2 squared should be the length squared. The length is square root of x squared plus y squared. So the square is again x squared plus y squared. And now we can multiply the left side in detail and see how it can agree with the right side. So x e1 plus y e2 times x e1 plus y e2. If we multiply that, we get x e1 times x e1. That makes x squared e1 squared. And we also get y e2 times y e2 makes y squared e2 squared. And then we get the mixed products, which have y and x and y. So if we first take x e1 times y e2, this gives us xy times e1 times e2. And then we have y e2 times x e1. That gives us another xy. But we cannot change the order. It is e2 times e1. That we must respect. And that should be here. That's a request for this new product, x squared plus y squared. Now, it's easy. We see that this can be fulfilled. Maybe first I write this once more as e1 squared plus y squared e2 squared plus. And this xy I take out of the bracket. e1, e2 plus E2 E1 equal x squared plus y squared. Yeah. So we say we want this new product, and this new product should have this property of r squared is the length of r squared. And if we try to work out what does that really mean, then the left side must be equal to the right side. And so that this can truly happen, we need that E1 squared is nothing but 1. So this is the first requirement. E1 squared is 1. And then E2 squared must also be 1. And that's fine, because the square of a vector under the new product should be the length squared. This is okay for E1 and E2. But then we have this extra term which disturbs very much. It's not on the right side. So the only consequence we can learn from that, draw from that, is that this must be 0. So that this must be 0, the term E1, E2 must be minus E2, E1. Then it can be 0. So we harvest that E1, E2 must be minus E2, E1 under this new product. And this corresponds geometrically to the following facts, that E1 has length 1, E2 as well has length 1, and the two vectors, they are, as you know, I have computed that, orthogonal. So E1 is orthogonal to E2. Yeah, I've computed that here. So E1 is orthogonal to E2. And now, what we can do, we can compute. Okay, first, maybe I will again give a minute for questions. Does anybody have a question about what I did now? Yes?
The second row.
Here?
Why is that?
Why is that? Yeah, so I go from here to over there. So we introduce an associate non-commutative, non-symmetric, and you see that this is really non-symmetric, product of vectors in R2. And this product, it's so dark because this is up there. For this product, we require that. So you start a new kind of mathematics by introducing a new product with a new requirement. And you can ask, why that? And the only answer I can give, because we want it, because we require it.
Because it works.
In the end, it has nice consequences, but it's a kind of arbitrary idea the mathematicians have come up with. But it is not, you cannot prove it. It's required.
It seems to work.
Yeah, it works in the end. It has many nice consequences, but it's something, an arbitrary setting or axiom by the human mind to say the new product we introduce should have this property. We request that. Okay. This was a very fundamental, very good question. Any other question? Here. Yes. Yeah, it comes from this requirement. So if the left side should be equal to the right side, then we have no choice but that E1, E2 plus E2, E1 is 0. And then we put with the minus sign this on the right side, and we get this as a consequence. Yeah. So this is nice for us because we find it on the right side. But this is a nuisance. We don't find it on the right side. So as a consequence of our requirement, we have to take this as a consequence and say, if this should be mathematically and philosophically consistent, if it should agree logically, then this term here must be 0. And the x in general is not 0, the y in general is not 0, these can be any real numbers. So what's only left, what can kind of save us out of this dilemma of having a quantity which appears but shouldn't be there, we can only say, okay, then this here, this combination must be 0. And if the combination is 0, then the first part must be minus the second part. Only then it can work. Yeah. We have this new thing. It's E1 times E2 in the new product. And we can also compute its square using this associativity. So let me do that. E1, E2 squared is E1, E2 times E1, E2. And in this new product, I do not need brackets because I have also requested it to be associative. So I should write brackets here and here, but I don't need to. Now, what I can do is to use this property. So I can change the order of E1 and E2 by changing the sign. I just apply this property. So I get minus E2 times E1 by changing the order here times E1 times E2. Now, I can put brackets wherever I want because I request that the new product is associative. So I decide arbitrarily, let me put brackets here and compute that product first, which is 1. So that I can do, and I find, so this is minus E2 times E2. And again, I know E2 squared is 1, so I find the whole result is very simple, minus 1. So if you take E1 times E2 and square it, you get minus 1, nothing but minus 1. And now I'll try, okay, could you follow this computation? So who has a question about this mystic computation? No? Okay, then I'll try to give a geometric interpretation of what that E1, E2 is. The square of this product here is negative. So E1, E2 is not a scalar because a scalar has a positive square. 3 squared is 9. It's not negative. And it is not a vector because every vector also has a positive square. So it is something new. But what is it? So it's a new type of quantity and it needs a new name. It's made from 2 vectors, so it's simply called bivector. Yeah. And it represents a piece of a plane, including orientation with sides E1 and E2. So I draw this. So imagine the plane of the blackboard. Then there is here unit length vector E1. And next perpendicular to it is the unit length vector E2. And then there's a piece of the plane, the unit square, here. And that is the bivector E1 times E2, and it has a product order. So you start with E1, and then you use E2. So that's basically how you go around it. And that's this product order for this bivector E1 times E2. And people find it cumbersome to always write E twice. So they introduce an abbreviation, a new symbol, and say, let me call this simply E1, 2. And then they don't use the vector symbol any longer, because it's not a vector any longer, it's a bivector. But if it has this double index, then it is kind of clear. Yeah. Okay, now this is, maybe I should even put it into writing. Yeah. So in writing it is the oriented plane area of the square. It's a square as you see. And it has the sides E1 and E2. Yeah. Okay. Does anybody have a question about this new object, which perhaps all of you have never seen before? No?
So that's a square,
Yes. Yes.
but it's not a normal square.
It's a normal square, but it has orientation. Because you see here, if you change the order of the vectors, you get a minus sign. So this small circular indicator tells you you go around like this. So first E1 and then E2, and then you get the square. It's like a winding sense. This is counterclockwise, and the other sense would be clockwise. The next thing, and this will be the last thing I do today, is simply define, based on that, what we have learned now, the Clifford product. So actually, I now say I define it, but later you learn it is just what we have constructed by this requirement. But in order that you can work with it until you understand it, I just say I define it. And these vectors are, as before, A and B. Then the Clifford product AB of these two vectors is A1 B1 plus A2 B2 plus A1 B2 minus A2 B1 times E1 2, and this is this bivector here. Yeah, and so at the moment it's just I define it like that. So it's the sum of something which is scalar and real, and something which is a scalar coefficient times bivector. So this whole thing is a bivector. And next time I'll talk more about it, and you learn more about what that is and what that is geometrically. Both have very nice geometric interpretations. Okay, so I finished here. 2 minutes for questions. Any more questions now? Like from here to here? Oh yeah. So maybe I will introduce an intermediate step. So this is clearly E1, E2 times E1, E2. But I'm free now to use this law here to change the order. So this is minus E2, E1, E1, E2. And because the product is required to be associative, I can drop all the brackets. And I get, from this one is minus E2, E1, E1, E2. And I have dropped all the brackets, but I can arbitrarily introduce new brackets. And that's what happens here. I take this expression and I insert new brackets here, indicating I first want to multiply E1 with E1, which I know is 1. And therefore I get as a leftover only minus E2 times E2. Okay, you're welcome. I'll be very happy to answer your questions. So it seemed you didn't learn a lot, but believe me, you learned a lot today. And if you don't understand it right away, don't worry. This is something very interesting and very new, I think. So then, if you didn't understand it, ask questions about it. Okay, so I look forward to see you next time then. Goodbye.